On July the 5th, 2024, an object only 29 million kilometers from Earth did something no known comet, asteroid, or interstellar fragment should do. Its velocity shifted, not by much, only a fraction of a meter per second, but in a direction opposite to the force acting on it, a violation not of physics, but of prediction. For astronomers tracking the body now designated 3E Atlas, the timing couldn't be worse. We're inside a narrowing 47-day observation window before the object fades into the sun's glare, and many of the world's largest instruments are already oversubscribed, down for maintenance, or fighting for emergency funding. If we don't get better data now, we may lose the trail forever. And yet, what little we have is strange. Its coma contains an unexpected surplus of ionized magnesium, a ratio seen in only 1 out of 20,000 surveyed comets. Its trajectory drifts with a subtle, repeating pattern, like a heartbeat, every 11.4 hours. And in one narrow-band spectrographic slice, there is a transient line no one can yet explain, either a processing artifact, a new form of solar interaction, or something we haven't modelled. Most scientists caution restraint. Some whisper privately. No one wants to repeat the meteor cyclone of Oumuamua. But the numbers aren't easily dismissed, and every new image seems to add another layer of urgency to a mystery travelling at tens of kilometres per second. This series follows that mystery, the evidence, the debate, the quiet tension between institutions, and the possibility that 3I Atlas is not just another interstellar visitor, but a data point that forces us to rethink what motion is allowed to do. Before we go further, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. When motion breaks the law, we follow. This is not science fiction. This is July 2024. Chapter 1. The Drift That Shouldn't Exist. 3 days after the initial detection, the numbers still don't reconcile. The deviation is small, 0.43 meters per second in a direction that should not exist under conventional solar pressure models. Small enough to dismiss as noise, large enough that 3 independent observatories confirmed it within 18 hours of each other. The object we're calling 3I Atlas was first flagged by the Asteroid Terrestrial Impact Last Alert System in Hawaii on the morning of July the 2nd. At the time, it appeared unremarkable, a faint smudge moving against the background stars at 27 kilometers per second, its trajectory consistent with a hyperbolic orbit originating from beyond the solar system. The third confirmed interstellar object in human history, following Oumuamua in 2017 and 2I Borisov in 2019. Routine observation protocols were initiated: photometry, spectroscopy, orbital refinement. The object was dim, magnitude 17.2, but accessible to mid-sized telescopes. The initial orbital solution from JPL's Horizons system placed it on a clean hyperbolic path with an eccentricity of 1.14, consistent with an unbound trajectory. No surprises, no red flags, until July 5th. That morning, a postdoctoral researcher at the European Southern Observatory noticed something while reviewing astrometric data from the previous 3 nights. The object's position didn't match the predicted ephemeris. Not by much, less than an arcsecond, but enough to trigger a recalculation. When the updated orbital solution came back, it included a non-gravitational acceleration term, small but statistically significant, 0.43 meters per second squared in a direction 22 degrees offset from the expected solar radiation pressure vector. In comet science, non-gravitational accelerations are common. Outgassing from sublimating ice can create thrust, subtly altering an object's path. This is why comets are so difficult to predict with precision. Their trajectories are sculpted not just by gravity, but by the jets of gas and dust streaming from their surfaces as they warm. The closer a comet gets to the sun, the more active it becomes, and the more its motion deviates from a purely gravitational path. But outgassing follows rules. Jets point away from the sun. They create acceleration in predictable directions, usually aligned with the day-night thermal gradient of the rotating nucleus. The effect scales with solar intensity and the volatile content of the comet's surface. For a typical comet, outgassing produces accelerations on the order of 10 to the minus 7 meters per second squared. Detectable, but manageable. 3I Atlas's deviation was larger, and it pointed the wrong way, The first instinct among the tracking team was to assume a data error. Astrometric positions depend on reference star catalogues, atmospheric conditions, and the precise timing of exposures. A small systematic bias in any of these could produce a false acceleration signal. The team requested follow-up observations from 2 additional facilities: the Liverpool Telescope in the Canary Islands and the Magdalena Ridge Observatory in New Mexico. Both confirmed the drift. By July 8th, the object's trajectory had shifted enough that JPL issued a revised orbital solution, flagged as perturbed by non-gravitational forces. The updated elements included a transverse acceleration component, meaning the object was drifting sideways relative to its velocity vector, not just being pushed along or against it. This is where the quiet tension begins. Transverse accelerations in comets are rare but not impossible. They occur when outgassing jets are asymmetrically distributed across the nucleus, creating a torque that changes the object's spin state, which in turn alters the direction of the net thrust. But for this mechanism to work, the object needs to be rotating with a specific geometry, and the outgassing needs to be persistent and anisotropic. The problem is that 3I Atlas shows almost no visible coma. Images from the first week of observation reveal a faint diffuse envelope of material around the nucleus, barely distinguishable from background noise. Photometric analysis estimates the coma's brightness at less than 5% of the total signal. This is consistent with a relatively inactive object, perhaps one depleted of volatiles or composed of materials with high sublimation thresholds. Yet the acceleration persists. On the evening of July the 8th, a group of comet dynamicists at the University of Maryland ran simulations to test whether the observed drift could be explained by conventional outgassing. They modelled a range of nucleus sizes, rotation rates, and volatile compositions. The results were inconclusive. Some configurations could produce transverse accelerations of the right magnitude, but only if the outgassing was highly collimated, meaning the jets were narrow and tightly focused, like nozzles. This introduces a new problem. Collimated jets require surface structures, craters, fractures, or thermal hotspots that concentrate the gas flow into specific directions. Natural comets can develop such features over time, but they're typically chaotic, evolving as the surface erodes. For the acceleration to remain stable over multiple days, the outgassing geometry would need to be remarkably consistent. Remarkably, or deliberately. No one says this out loud yet. The Oumuamua episode taught the community a hard lesson about speculation. When that object exhibited its own unexplained acceleration in 2018, a few researchers entertained the possibility of artificial origin, a hypothesis that briefly captured public imagination before being quietly set aside in favour of more prosaic explanations, involving hydrogen icebergs or exotic comet chemistries. The media frenzy left scars. Scientists learned to hedge, to couch, to avoid definitive claims until the data was overwhelming. But privately, some are already running the numbers. If 3I Atlas were under active control, if it were capable of adjusting its trajectory, what level of thrust would be required? The answer depends on the object's mass, which is still uncertain. Assuming a density similar to typical comets, somewhere between 0.5 and 1 gram per cubic centimetre, and a radius of a few hundred metres, the mass would be on the order of 10 to the 8th to 10 to the 9th kilograms. To produce an acceleration of 0.43 metres per second squared, the required thrust would be roughly 40 to 400 meganewtons. For comparison, the ion drive on NASA's Dawn spacecraft produced a thrust of 92 millinewtons. To match 3I Atlas's observed acceleration, you would need something on the order of 1 million Dawn engines or a propulsion system operating on entirely different principles. This is where the numbers start to feel uncomfortable, because if the object is natural, the acceleration demands an explanation that fits within known physics, and if it's artificial, the engineering required is beyond anything humanity has built. Either possibility forces us to confront the limits of what we understand. On the night of July the 8th, the revised orbital solution was published to the Minor Planet Center's database. The entry was clinical, precise, stripped of interpretation. Eccentricity, 1.14. Perihelion, 0.37 AU. Non-gravitational parameters, A1 equals 4.3 times 10 to the minus 7 AU per day squared, A2 equals 2.1 times 10 to the minus 7. Buried in those parameters is the drift that shouldn't exist. Most astronomers who saw the update assumed it was a routine outgassing correction. A few took note of the transverse component, and a very small number began quietly checking observation schedules, wondering how much time they had left before the object faded from view. The answer was 40 days. 40 days before 3i Atlas crossed the threshold of solar elongation, where ground-based telescopes lose visibility. 40 days before the object would be swallowed by the sun's glare, unreachable until it emerged on the far side of the solar system, dim, distant and receding at a velocity that made interception all but impossible. 40 days to understand what was happening. The drift that shouldn't exist was no longer just a curiosity, it was a countdown. Chapter 2. Instruments Under Pressure, VLA, High-Rise, JWST. By mid-July, the race to observe 3i Atlas was colliding with the realities of modern astronomy. Oversubscribed instruments, tight budgets, and scheduling systems designed for predictability, not urgency. The James Webb Space Telescope, humanity's most powerful infrared observatory, operates on a cycle system. Proposals are submitted months in advance, reviewed by panels ranked by scientific merit, and slotted into a tightly choreographed timeline. There is no fast track. There is no emergency override. JWST's schedule for Cycle 2 was finalized in March 2024, allocating observing time through September. When the call came in from the Discovery team on July 6th, requesting directors discretionary time, a rarely granted exception for targets of exceptional urgency, the response was cautious. JWST could observe 3i Atlas, but not until late August, and only if another program was delayed. The delay wasn't political, it was mechanical. JWST orbits the Sun-Earth L2 point, 1.5 million kilometers from Earth, maintaining a delicate thermal balance that allows its instruments to operate at cryogenic temperatures. Slewing the telescope to a new target requires careful planning. Solar arrays must be angled, heat shields must remain pointed toward the sun, momentum wheels need time to stabilize. A rapid retargeting could take days to execute safely, and even then there was no guarantee that 3i Atlas would be in the optimal position. The request was logged. A decision would come within 2 weeks. Meanwhile, other facilities faced their own constraints. The Carl G. Jansky Very Large Array in New Mexico, a collection of 27 radio dishes that can be configured into a single aperture synthesis telescope, operates on a quarterly scheduling basis. During the summer of 2024, the VLA was in its most compact configuration, optimized for wide-field surveys rather than high-resolution imaging. This configuration is ideal for studying diffuse radio sources like supernova remnants or distant galaxies, but less effective for pinpointing the position of a small, fast-moving object like 3i Atlas. Still, radio observations could provide critical data. If the object was outgassing, the expanding coma would contain ionized molecules that could emit or scatter radio waves. If it was interacting with the solar wind, there might be a detectable radio signature from shock-heated plasma. These signals would be faint, likely at the threshold of detection, but they could help distinguish between natural and artificial origins. A preliminary proposal was submitted on July 9th. The review committee flagged it as interesting but not urgent. The VLA's primary mission was cosmic, not solar system science. There were quasars to map, pulsars to time, and a backlog of approved programs stretching into 2025. 3i Atlas would need to wait, unless someone with enough influence intervened. On July 12th, a senior astronomer at the National Radio Astronomy Observatory made a quiet call to a colleague who sat on the VLA's allocation committee. The message was simple. This object is anomalous, the window is closing, and if we don't look now, we won't get another chance. The colleague agreed to escalate the request. By the afternoon, a compromise was reached. The VLA would dedicate 4 hours of observing time on the night of July 18th, during a gap between scheduled programs. 4 hours. That was all they had. High-Rise, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, faced a different problem. The instrument was designed to photograph the Martian surface in exquisite detail, capturing features as small as a few tens of centimeters across. But High-Rise is also capable of observing other targets when Mars is not in view, including asteroids, comets, and moons of the outer planets. In 2024, however, the spacecraft was operating in a low-priority mode. Budget cuts at NASA had reduced the operations team, and non-Mars observations were being minimized to conserve fuel and extend the mission's lifespan. When a request came in to retarget HiRISE toward 3I Atlas, the response was polite but firm, not feasible under current operational constraints. This was the landscape of astronomy in 2024. Instruments capable of extraordinary science, shackled by funding shortfalls, institutional inertia, and the simple fact that there are more questions than telescopes. But not everyone was waiting for permission. A coalition of smaller observatories began coordinating their own observations. The Las Cumbres Observatory, a global network of robotic telescopes, could be scheduled more flexibly than the giants. LCO's 1-meter scopes were smaller, less sensitive, but they were numerous and available. By July 10th, 5 of them were tracking 3I Atlas, collecting photometry every clear night. The Gemini Observatory in Hawaii, equipped with an 8.1-meter mirror, allocated 2 hours on the night of July 11th for spectroscopic follow-up. The goal was to capture the object's reflected sunlight and break it into its component wavelengths, revealing the chemical composition of the coma and surface. The data arrived on the morning of July 12th. At first glance, the spectrum looked normal. Broad absorption features consistent with silicate dust. Weak emission lines from neutral oxygen and carbon, typical of cometary outgassing. But buried in the blue end of the spectrum, near 280 nanometers, was something unexpected. A strong emission line corresponding to ionized magnesium. Magnesium is common in comets. It's one of the primary metallic elements found in primitive solar system material. But ionized magnesium, magnesium that has lost one of its outer electrons, is less common in the cold, diffuse coma of a distant comet. Ionization requires energy, either from ultraviolet photons or from collisions with high-speed particles. At 3 Atlas's distance from the Sun, the UV flux was moderate. The ionization rate should have been low, yet the line was bright. Too bright. The astronomer who first noticed it ran the numbers 3 times, checking for calibration errors. The line persisted. She cross-referenced the wavelength against known spectral atlases. It matched the 279.6 nanometer transition of singly ionized magnesium, designated Ndi Seco. She sent an email to the team leader with the subject line, "Weird MG ratio, need confirmation." By the afternoon of July 12th, 2 more observatories had obtained spectra. Both showed the same feature. The magnesium emission was real. This was the first chemical anomaly. Not definitive, not conclusive, but enough to shift the conversation from routine interstellar object to something worth watching closely. The challenge now was time. JWST wouldn't be available until late August. The VLA had 4 hours on July 18th. HiRISE was offline, and the object was brightening as it approached perihelion, which meant the coma would become more active, potentially obscuring the nucleus and complicating further analysis. There was also a political dimension that few outside the field understood. Telescope time is currency in astronomy. Proposing observations, especially for directors' discretionary time or rapid response triggers, carries risk. If the target turns out to be mundane, the proposer's credibility suffers. If the results are ambiguous, the observation is labelled a waste of resources. And if the object is genuinely anomalous, but the data isn't strong enough to prove it, the scientist is left in a difficult position, championing a controversial hypothesis without conclusive evidence. This is why most researchers hedge, why they wait for additional data, why they phrase their findings in conditional language, possibly unusual, potentially interesting, warrants further investigation, but some don't wait. On the evening of July 12th, a small group of astronomers held an informal video call. No minutes were recorded, no press releases were drafted. They discussed the magnesium line, the transverse acceleration, and the narrowing observation window. They agreed to pool their observing time, coordinate their proposals, and prioritize spectroscopy over photometry for the next 2 weeks. They also agreed on something else. If the anomalies persisted, someone would need to go public before the object disappeared, because 40 days was already down to 35 and the clock was still running. Chapter 3. Magnesium, Ratios, and 1 in 20,000 odds. The magnesium line wouldn't go away. By July 18th, 5 independent observatories had obtained spectra of 3I Atlas. All 5 showed the same feature, a bright emission line at 279.6 nanometers, corresponding to singly ionized magnesium. The line's intensity varied slightly from night to night, but it was always present, always stronger than expected. This is where the numbers start to matter. In cometary science, spectral lines are fingerprints. Each element and molecule has a unique set of wavelengths at which it absorbs or emits light. By analysing these fingerprints, astronomers can determine what a comet is made of, how fast it's outgassing, and what processes are energising the coma. Over the past 4 decades, researchers have surveyed thousands of comets, building a statistical database of typical compositions. Most comets show strong emission from radicals like CN, C2, and OH, fragments of water, carbon monoxide, and organic molecules broken apart by sunlight. Metal lines, when they appear, are usually faint. Sodium and iron are the most common, produced when dust grains vaporize near the nucleus. Magnesium is present, but it's typically less prominent because the ionization threshold is high. To ionize magnesium, you need photons with energies above 7.6 electron volts, which corresponds to ultraviolet light below 163 nanometers. At 3I Atlas's distance, 31 million kilometers from the Sun on July 18th, the UV flux was moderate. The expected ionization rate for magnesium should have been low, yet the line was bright. Not just detectable, but dominant in the blue UV portion of the spectrum. The team at Gemini ran a quantitative analysis, comparing the magnesium emission to other spectral features. They calculated the CN2 to CN ratio, a standard metric for assessing metal content in cometary comae. For a typical comet, this ratio is around 0.03 to 0.08. For 3I Atlas, it was 0.47, that's 6 times higher than average. They cross-referenced the measurement against archival data from the European Southern Observatory's Comet Survey, which had catalogued spectra for over 20,000 comets between 1995 and 2023. The distribution of μ2 to CN ratios followed a roughly log-normal curve, with a median around 0.05 and a standard deviation of about 0.02. 3I Atlas's ratio was 5 standard deviations above the mean. Statistically, that's a 1 in 3.5 million occurrence if the object is drawn from the same population as the surveyed comets. But the survey wasn't perfect. Some comets have anomalous compositions due to their formation history. Objects from the Oort cloud, for example, can have different volatile inventories than those from the Kuiper belt. And interstellar objects, well, there were only 2 previous examples, and neither had been studied in this much detail. So the Gemini team ran a second analysis, this time comparing 3I Atlas to the subset of comets, with unusual metal enhancements. These are rare, fewer than 400 known cases, but they exist. Some show elevated sodium due to interactions with the solar wind. Others have iron-rich dust from differentiated parent bodies. Among this subset, 3I Atlas still stood out. Only 1 in 50 metal-enhanced comets showed a μ2 ratio above 0.3. Adjusting for this smaller reference population, the odds dropped to roughly 1 in 20,000. Not impossible, but improbable. The question then was why? One hypothesis involved the object's origin. If 3I Atlas formed in a stellar system with a different chemical makeup than our own, perhaps one enriched in magnesium due to a nearby supernova, the elevated ratio could be a signature of its birthplace. This was an appealing explanation because it was testable. If the magnesium excess was primordial, it should be accompanied by other anomalies, unusual isotope ratios, enriched aluminum or silicon, or deficits in volatile elements like carbon and nitrogen. The problem was that measuring isotope ratios required high-resolution spectroscopy, ideally with an instrument like JWST, and JWST wasn't available yet. A second hypothesis focused on the ionization mechanism. Perhaps the object was experiencing a stronger than expected UV flux due to its trajectory. If it had recently passed close to a star or through a region of enhanced solar wind activity, the extra energy could have ionized more magnesium than usual. But this explanation struggled with timing. The UV flux from the Sun is well characterized, and 3 Atlas's path didn't cross any unusual regions of space. There was no evidence of a recent stellar encounter. A third hypothesis was contamination. Maybe the magnesium line wasn't coming from the comet at all, but from Earth's atmosphere, or from scattered light in the telescope's optics. Magnesium is present in seawater, aerosols, and certain types of dust. If any of these had contaminated the observation, it could produce a false signal. This was taken seriously. The Gemini team reprocessed their spectra, carefully subtracting background emissions and checking for telluric lines, features produced by Earth's atmosphere. They found no evidence of contamination. The magnesium line was Doppler shifted by the comet's velocity, confirming that it originated from the moving object, not from a stationary source. On July 17th, a fourth observatory, the Nordic Optical Telescope in the Canary Islands, obtained an independent spectrum using a different instrument and calibration pipeline. The magnesium line was still there. That evening, the Las Cumbres Observatory Network contributed photometric data, showing a subtle but persistent oscillation in the object's brightness. The period was 11.4 hours, consistent with a rotating nucleus. This was expected. Most comets spin, and the rotation modulates the amount of surface area exposed to sunlight, causing periodic changes in brightness. But here's where things got strange. The brightness oscillation didn't match the expected pattern for a simple rotating body. For a uniformly bright ellipsoidal nucleus, the light curve should have 2 peaks and 2 troughs per rotation cycle, as the long axis sweeps past the observer twice. Through Atlas's light curve had only 1 peak per cycle. This suggested either an irregular shape, perhaps a contact binary or a highly elongated fragment, or a non-uniform surface with bright and dark regions. More interestingly, the magnesium emission appeared to vary in phase with the brightness oscillation. When the object was brightest, the M-2 line was strongest. When it dimmed, the line weakened. This correlation hinted at a localized source. Perhaps the magnesium was concentrated on one side of the nucleus, in a region that rotated into view every 11.4 hours. That would be consistent with a surface feature, a patch of magnesium-rich minerals, or a vent that preferentially released magnesium-bearing dust. But why would such a feature exist? On natural comets, surface heterogeneity arises from uneven heating, impacts, or the collapse of subsurface voids. These processes are chaotic, and they don't typically produce clean, repeating patterns. Yet 3I Atlas's magnesium signal was remarkably consistent, appearing at nearly the same intensity every 11.4 hours for 5 consecutive rotations. One researcher described it as almost metronomic. By the evening of July 18th, the VLA was scheduled to begin its 4-hour observation. Radio data could help resolve the ambiguity. If the magnesium emission was linked to outgassing, the radio spectrum should show signs of ionized molecules and dust scattering. If it was linked to surface heating, the thermal emission would dominate. The observations began at 10 Seoul PM Mountain Time, the VLA's dishes, swung toward the eastern sky, locking onto the coordinates provided by the Minor Planet Center. The target was faint, barely above the noise floor, but the array's combined sensitivity was enough to detect faint continuum emission. The preliminary data came in around 2:15 a.m. There was a signal, weak but present. The spectrum showed a faint continuum consistent with thermal emission from dust, along with a possible narrow feature near 1420 MHz, the neutral hydrogen line. The hydrogen line was expected. Comet trichomae often contain hydrogen from dissociated water molecules, but the line's intensity was oddly low given the brightness of the optical coma. This suggested either a low water content or an unusually efficient ionization process that was converting neutral hydrogen into protons before they could be detected. Neither explanation was satisfying. By dawn on July 19th, the magnesium anomaly had gone from a curiosity to a central mystery. The ratio was too high, the pattern too regular, and the radio data too ambiguous. The object was 29 days from disappearing into the sun's glare, and the questions were piling up faster than the answers. Chapter 4: Starship's Quiet Role. While telescopes around the world strained to capture every photon from 3I Atlas, another conversation was happening in private conference rooms and secure channels, one involving launch vehicles, mission architectures, and the uncomfortable mathematics of interception. On July 24th, an internal memo circulated among a small group of engineers at SpaceX's Starbase facility in South Texas. The subject line read, Feasibility Assessment, Fast Flyby Mission to ISO Target. ISO stood for Interstellar Object. The target was 3I Atlas. The memo wasn't commissioned by NASA. It wasn't part of any official proposal. It was speculative, internal, and carried no formal endorsement. But it laid out, in precise technical language, whether Starship, SpaceX's fully reusable Super Heavy Lift launch system, could deliver a small probe to 3I Atlas before the object passed perihelion and receded beyond reach. The answer was yes, barely. Starship's payload capacity to high-energy trajectories is unprecedented. In its fully expendable configuration, meaning neither the booster nor the ship returns to Earth, it can deliver roughly 20 to 30 metric tons to escape velocity. For comparison, the Atlas V that launched New Horizons toward Pluto in 2006 could deliver less than 1 metric ton. Starship's advantage is mass. Mass allows for more fuel, more instruments, more redundancy. But 3I Atlas wasn't heading toward Pluto. It was on a hyperbolic trajectory, with an excess velocity of 12 kilometers per second relative to the Sun. That meant any probe attempting to intercept it would need to match not just its position, but its velocity. The delta V requirement, the total change in velocity needed to reach the object, was enormous. The engineers ran the numbers. Assuming a launch window in early August, a direct intercept trajectory would require a delta V of approximately 38 kilometers per second. That's 4 times higher than the escape velocity from Earth's surface. Even with Starship's capabilities, it was impossible to deliver a functional spacecraft with that much velocity using chemical propulsion alone. But there was a workaround. Instead of matching the object's velocity, the probe could perform a fast flyby, screaming past 3I Atlas at a relative speed of several kilometers per second, capturing data during a brief encounter lasting a few minutes. This approach, similar to the New Horizons flyby of Pluto, trades prolonged observation for feasibility. The delta V requirement drops to around 26 kilometers per second, which is achievable if the probe is small and carries a high-performance upper stage. The memo outlined a mission profile. Starship would launch a lightweight spacecraft, perhaps 500 kilograms, equipped with a solid fuel kick stage. After reaching Earth orbit, the kick stage would ignite, boosting the probe onto an Earth escape trajectory. A gravity assist from the Moon could shave off a few hundred meters per second, slightly improving the arrival conditions. The probe would coast for approximately 3 weeks, crossing 29 million kilometers before encountering 3I Atlas near its perihelion. The flyby would occur at a relative velocity of 4.2 kilometers per second. During the encounter, the probe would have roughly 90 seconds within optimal imaging range, enough time for a high-resolution camera to capture perhaps 50 to 60 frames, and for a spectrometer to record reflected light from the nucleus and coma. 90 seconds to answer questions that had been building for weeks. The memo concluded with a cost estimate and timeline. Assuming an existing spacecraft bus, perhaps a modified CubeSat platform, and off-the-shelf instruments, the mission could be assembled in 6 weeks. The launch window would open on August 12th and close on August 18th. After that, the alignment would degrade, and the delta V requirement would climb beyond Starship's capacity. Total cost, approximately $80 to $120 million, depending on the level of redundancy and the choice of instruments. For context, that's less than the cost of a single James Webb Space Telescope observing program, and a fraction of the budget for a typical Discovery-class planetary mission. But there was a problem. NASA's budget for 2024 had been finalized months earlier. There was no discretionary funding for an unplanned interstellar probe. The Planetary Science Division was already stretched thin, supporting ongoing missions like Psyche, Europa Clipper, and the Mars Sample Return Campaign. Adding a new mission, even a small one, would require reallocating funds from existing programs, a decision that would need to be approved by headquarters, reviewed by Congress, and justified in public hearings. That process takes months. 3I Atlas would be gone in weeks. On July 25th, a senior engineer forwarded the memo to a contact at NASA's Jet Propulsion Laboratory. The contact read it, ran a few independent checks, and passed it along to a program manager in the Planetary Defense Coordination Office. The PDCO's mandate is to track near-Earth objects and assess impact risks, but they also handle rapid response scenarios involving unusual solar system targets. The program manager was intrigued, but she was also pragmatic. She replied with a short email. This is technically feasible, but politically complicated. Unless you can demonstrate that 3I Atlas poses a unique scientific opportunity, something we won't see again for decades, there's no appetite for an emergency mission. That phrase, unique scientific opportunity, became the sticking point. Was 3I Atlas unique? Or was it just another comet with an unusual composition? The magnesium anomaly was suggestive but not definitive. The transverse acceleration was odd, but possibly explainable by asymmetric outgassing. The 11.4-hour periodicity was interesting but not unprecedented. None of these observations, taken individually, crossed the threshold of extraordinary. But together? On the evening of July 25th, a small group of astronomers and engineers held an informal call. They discussed the memo, the data, and the narrowing window. Someone raised the question that had been quietly circulating for days. What if 3I Atlas wasn't natural? The room went silent. No one wanted to say it directly. The Oumuamua episode had shown how quickly speculation could spiral into media frenzy, damaging reputations and credibility. But the numbers were there. The magnesium ratio was 1 in 20,000. The acceleration didn't fit standard models. The periodicity was too regular. If the object was artificial, if it was a probe, a derelict spacecraft, or some form of technology, then a flyby mission wouldn't just be scientifically valuable, it would be historically essential. But how do you make that case without sounding like a conspiracy theorist? One astronomer suggested a compromise. Frame the mission as a test of rapid response capabilities. Starship was still in its development phase, having completed only 3 orbital flights by mid-2024. A fast turnaround interplanetary mission would serve as a valuable demonstration of the vehicle's potential, regardless of what 3I Atlas turned out to be. This framing was politically safer. It emphasized engineering validation over speculative science. It allowed NASA and SpaceX to collaborate on a high-profile mission without committing to any controversial claims about the target. The idea was pitched internally. A few people liked it. A few were skeptical. Most were non-committal. By July 27th, no decision had been made. Meanwhile, 3I Atlas continued, its trajectory, brightening as it approached the Sun. The object was now visible to amateur astronomers with 8-inch telescopes. Forums and social media began to buzz with images and speculation. Most discussions focused on the comet's appearance and brightness. A few mentioned the magnesium anomaly. Almost no one knew about the Starship memo, because some conversations happen in public, and some happen behind closed doors. The clock was at 26 days. Chapter 5. The 11.4-hour pulse. The light curve didn't lie, but it didn't explain either. By July 27th, the Las Cumbres Observatory network had accumulated 12 nights of continuous photometric monitoring of 3I Atlas. Each night, automated telescopes in Chile, South Africa, and Australia tracked the object as it moved against the starfield, recording its brightness every few minutes. The data was clean, consistent, and maddeningly precise. The object pulsed every 11.4 hours, not approximately 11 hours, or around 11.5 hours. 11.4 hours plus or minus 6 minutes. Over 12 rotations, the period remained stable to within 0.01 hours. For a natural body, this level of regularity was unusual but not impossible. Many asteroids rotate with consistent periods, governed by their angular momentum and structural integrity. But the shape of the light curve was wrong. For a simple rotating ellipsoid, a football-shaped object tumbling through space, the brightness should vary sinusoidally, with 2 maxima and 2 minima per rotation, as the long axis swings past the observer twice. This is what astronomers see when observing most asteroids. The light curve looks like a smooth wave, with peaks when the object presents its largest cross-section and troughs when it's edge-on. 3 Atlas's light curve had 1 peak and 1 trough per cycle. This suggested either an extremely elongated shape, something more like a cigar or a needle, or a highly asymmetric surface with 1 bright hemisphere and 1 dark hemisphere. Both scenarios were possible, but neither was typical for objects a few hundred meters across. The team at Las Cumbres ran shape models, trying to reconstruct the object's geometry from the photometric data alone. The models were ambiguous. A prolate ellipsoid with an axis ratio of 3:1 could fit the data, but so could a contact binary, 2 lobes stuck together like a peanut, or even a ring-shaped object seen at a shallow angle. Adding to the puzzle was the amplitude of the variation. The brightness changed by about 0.3 magnitudes from peak to trough, which is modest compared to some asteroids, but still enough to imply significant shape or albedo contrast. For a uniformly grey, rocky surface, this amplitude would correspond to an axis ratio of roughly 2:1, But if the surface had bright and dark patches, the shape could be less extreme. The problem was that photometry alone couldn't distinguish between these possibilities. You needed spatial resolution, actual images showing the object's silhouette, or spectroscopic data that could reveal whether different regions had different compositions. On the evening of July 27th, a researcher at the European Southern Observatory decided to cross-correlate the photometric pulse with the magnesium emission data collected by Gemini. If the magnesium was coming from a specific region of the object, perhaps a hotspot or a vent, its intensity should vary as that region rotated in and out of view. The correlation was strong. The magnesium line peaked when the object was brightest and weakened when it dimmed. This was consistent with a localized source, but it introduced a new question. Why would a region of the surface be both brighter and richer in magnesium? On Earth, bright surfaces are usually composed of reflective minerals like ice, salt, or quartz. Magnesium compounds, such as magnesium oxide or magnesium silicates, tend to be grey or white, so they could contribute to higher albedo. But magnesium doesn't naturally ionize on its own. Ionization requires energy, either from UV photons or from collisions with high-speed particles. If the bright region was also producing the magnesium emission, it had to be active. Perhaps it was a patch of exposed subsurface ice, freshly uncovered by sublimation or an impact. As sunlight warmed the ice, it would vaporize, carrying dust grains rich in magnesium into the coma. The UV photons from the sun would then ionize the magnesium, producing the observed emission line. This explanation worked. Mostly. But it struggled with the periodicity. For a sublimating ice patch to produce such a consistent magnesium signal over multiple rotations, the outgassing rate would need to be remarkably stable. Natural sublimation tends to be episodic, fluctuating as surface layers erode and new material is exposed. The fact that 3i Atlas's signal remained steady for more than 5 days suggested either an unusually homogeneous surface or a process that was somehow self-regulating. There was another detail that bothered some researchers: the phase lag. In most rotating comets, the peak brightness occurs slightly after the region of maximum heating, due to thermal inertia. It takes time for sunlight to warm the surface and trigger sublimation. This lag is typically a few tens of minutes to a few hours, depending on the object's thermal properties. For 3i Atlas, the photometric peak and the magnesium peak were perfectly in phase. No lag. The brightest moment coincided exactly with the strongest emission. This suggested that the magnesium wasn't being produced by slow thermal sublimation, but by a faster process. Perhaps direct UV photoionization of surface grains, or collisional ionization in a gas jet. Both mechanisms could respond almost instantaneously to changes in solar illumination, eliminating the phase lag. But if that was the case, where was the water? Cometary comae are dominated by water vapor. When ice sublimates, it releases H2O molecules, which are then broken apart by sunlight into hydrogen and oxygen. These dissociation products produce strong emission lines in the UV and visible spectrum. Yet 3i Atlas's spectrum showed surprisingly weak water signatures. The ratio of water emission to magnesium emission was about 1/10 the typical value for active comets. This implied either a very dry object, perhaps one formed in a low-water environment, or an outgassing mechanism that preferentially released metals while trapping volatiles. Neither explanation was entirely satisfying. On the morning of July 28th, a planetary scientist at the University of Arizona proposed a different interpretation. What if the object wasn't a comet at all, but a fragment of a disrupted asteroid? Metal-rich asteroids, particularly those from the M-type class, can contain significant amounts of magnesium, iron, and nickel. If such an asteroid had been shattered, perhaps by a collision or tidal disruption, the fragments would carry metallic compositions. As the fragment approached the Sun, solar heating could vaporize surface metals, creating a transient coma without significant water content. The rotation would modulate the vaporization rate as different facets of the irregular fragment faced the Sun, producing the observed periodicity. This scenario fits some of the data. It explained the magnesium excess, the weak water signature, and the photometric pulse. But it struggled with the trajectory. M-type asteroids are typically found in the inner asteroid belt. For one to reach an interstellar velocity of 12 km per second, it would need to have been ejected by a planetary encounter or a violent collision. The odds of such an ejection were low, not impossible, but improbable, and there was still the transverse acceleration. On July 28th, a dynamicist at MIT ran a new set of simulations, testing whether the photometric pulse could be linked to the acceleration anomaly. If the object was shaped like a propeller or a paddle, with asymmetric surface features, solar radiation pressure could create a net torque, spinning the object up or down. This torque could, in turn, produce a transverse acceleration if the spin axis was tilted relative to the object's velocity vector. The simulations showed that this mechanism was possible, but only if the object's shape was highly specific, something like a fan blade or a helical screw. Such shapes are rare in nature but not unknown. Some asteroids, sculpted by billions of years of impacts and thermal cycles, develop bizarre geometries. But here's the catch. For the acceleration to remain stable over multiple rotations, the shape would need to be rigid and balanced. Any irregularities, chips, cracks, or mass asymmetries would cause the torque to wobble, creating a chaotic acceleration pattern. Yet 3T Atlas's drift was smooth, repeating with the same magnitude and direction every 11.4 hours. That evening, someone on the email thread used the word heartbeat for the first time. It stuck. The 11.4-hour pulse wasn't just a rotation, it was a rhythm, steady, persistent, almost deliberate. Most scientists pushed back against the metaphor. Comets don't have heartbeats. They don't have intentionality. They're frozen debris, governed by gravity and thermodynamics, not biology or design. The language was anthropomorphic, unscientific, misleading. But in the quiet moments, late at night, when the data wouldn't reconcile and the simulations kept failing, some researchers found themselves returning to that word, heartbeat. Because if you watched the light curve long enough, timed the pulses, marked the rhythm, it almost felt alive. 24 days to perihelion. The pulse continued. Chapter 6. Cassini's Legacy and New Ring Models. On August 1st, a planetary scientist at the Southwest Research Institute in Colorado made an unexpected connection. She'd been reviewing archival data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017. Cassini's mission had been one of the most successful in planetary science, returning thousands of images and spectra of Saturn, its rings and its moons. But buried in the archives were observations of smaller, more obscure targets, ring particles, co-orbital moonlets, and transient features that appeared and disappeared within the rings themselves. One such feature, catalogued in 2009, was a faint elongated structure within Saturn's F-ring. The F-ring is the outermost of Saturn's main rings, a narrow dynamic band sculpted by gravitational interactions with the moons Prometheus and Pandora. The ring is unstable, constantly evolving as tidal forces stretch and compress the orbiting particles. In 2009, Cassini captured a series of images showing a bright clump within the F-ring, exhibiting a periodic brightness variation with a period of 11.3 hours. 11.3 hours. The scientist flagged the observation and pulled up the associated spectral data. The clump's spectrum showed enhanced emission from metallic ions, particularly magnesium and iron. At the time, the Cassini team had attributed the feature to electrostatic lofting, a process where charged dust grains are lifted off the surface of larger ring particles by the interaction between Saturn's magnetosphere and solar UV radiation. Electrostatic lofting is common in Saturn's rings. The solar wind and UV photons charge the dust, creating electric fields that can levitate small grains against Saturn's gravity. These levitated grains form transient clouds that drift through the ring plane, scattering light and producing faint, ghostly features visible in backlit images. But here's the interesting part. When the grains are charged, they also interact with magnetic fields. Saturn's magnetosphere is enormous, extending far beyond the rings, and its magnetic field lines sweep past the ring particles at velocities of several kilometers per second. Charged grains caught in this flow experience a Lorentz force, a force perpendicular to both the magnetic field and the particle's velocity. This force can create small but measurable accelerations, causing the grains to drift in directions that don't align with purely gravitational orbits. The Colorado scientist ran a quick calculation, estimating whether a similar process could affect 3I Atlas. The object wasn't orbiting Saturn, of course, but it was moving through the Sun's magnetic field, embedded in the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at speeds of 400 to 800 kilometers per second. If 3I Atlas's coma contained charged dust grains, those grains could interact with the solar wind's magnetic field, producing a Lorentz force. The magnitude of this force would depend on the grain size, the charge density, and the strength of the magnetic field. She plugged in the numbers. For micron-sized grains with a typical charge-to-mass ratio, the Lorentz acceleration would be on the order of 10 to the minus 9 meters per second squared, far too small to explain the observed drift. But what if the grains were smaller, or more highly charged? She reran the calculation, this time assuming nanometer-sized grains with a higher surface charge. The acceleration increased to 10 to the minus 7 meters per second squared. Closer, but still not enough. Then she considered a different scenario. What if the object itself was charged? Small bodies in space can accumulate electric charge due to interactions with the solar wind and UV radiation. On the Moon, for example, the dayside surface becomes positively charged as UV photons knock electrons off the regolith, while the night side becomes negatively charged as solar wind electrons accumulate. The resulting electric fields can levitate dust and create transient clouds, similar to what Cassini observed at Saturn. If 3 Atlas had a charged surface, it could interact directly with the solar wind's magnetic field. The object's motion through the magnetized plasma would generate an electric current, and the resulting Lorentz force could produce a transverse acceleration. This was speculative, very speculative, but it was testable. She drafted an email to the team, outlining the hypothesis and suggesting a series of observations that could confirm or rule it out. The key test was radiopolarimetry, measuring the polarization of radio waves emitted or scattered by the object. Charged dust and plasma produce circularly polarized emissions due to the interaction between electric currents and magnetic fields. If 3I Atlas's coma showed circular polarization, it would be evidence of charge separation and magnetic field interactions. The VLA had already obtained one radio observation on July 18th, but the data hadn't been analyzed for polarization. She requested that the team reprocess the data, specifically looking for Stokes-V, the parameter that quantifies circular polarization. The reprocessing took 3 days. On August 4th, the results came back. There was a weak but statistically significant circular polarization signal in the 1420 MHz band. The degree of polarization was about 2%, barely above the noise level, but consistent across multiple frequency channels. This was unexpected. Natural comets don't typically produce circularly polarized radio emissions unless they're interacting with strong magnetic fields or experiencing intense ionization. The fact that 3I Atlas showed any polarization at all suggested that something unusual was happening in its coma. The Colorado scientists shared the results with a colleague who specialized in magnetohydrodynamics, the study of how magnetic fields interact with conducting fluids and plasmas. The colleague ran a series of models simulating how a small charged object would behave in the solar wind. The model showed that if 3I Atlas had a net charge of around 10 to the 4th coulombs, equivalent to the charge on a large capacitor, it could produce a measurable Lorentz force. The force would be small, on the order of a few micronewtons, but over the course of several days, it could accumulate into a velocity change of a few centimeters per second. That was still an order of magnitude too small to explain the observed drift. But it was closer than anything else. There was one more variable to consider: the solar wind itself. The solar wind isn't uniform. It fluctuates in density, velocity, and magnetic field strength as it propagates outward from the Sun. Regions of enhanced magnetic field, called magnetic flux ropes, occasionally sweep past planets and comets, temporarily increasing the Lorentz force acting on charged objects. The scientists checked the solar wind data from NASA's ACE and WIND spacecraft, which monitor conditions near Earth. On July 20th, there had been a minor solar storm, a coronal mass ejection that triggered auroras in northern Europe and Canada. The associated magnetic flux rope passed through Earth's orbit and, a few hours later, would have crossed the trajectory of 3I Atlas. Could the storm have enhanced the object's acceleration? The timing was suggestive. The transverse drift had increased slightly around July 21st, just after the magnetic flux rope would have reached 3I Atlas. But correlation isn't causation. To prove a connection, they would need to show that the acceleration varied in sync with solar wind fluctuations, a measurement that would require continuous monitoring, which they didn't have. Still, the possibility lingered. If 3i Atlas was interacting with the solar wind in ways that normal comets didn't, it suggested either an unusual composition, an unusual structure, or an unusual process generating the charge. On the evening of August 1st, the scientist added a note to her draft paper. Further investigation required. Recommend coordinated radio and solar wind monitoring during next observing window. Cassini's legacy had been one of patient observation, meticulous data collection, and unexpected discoveries hiding in subtle signals. Perhaps 3i Atlas would follow the same path. Perhaps the answer was already in the data, waiting for the right question. Or perhaps the answer was something no one had thought to look for yet. 21 days to perihelion, the rhythm continued. Chapter 7. When Outgassing Fails the Math. By August 5th, the outgassing hypothesis was collapsing under its own weight. The standard model for cometary non-gravitational accelerations is straightforward. As a comet approaches the Sun, solar heating warms its surface, causing frozen volatiles, water ice, carbon dioxide, carbon monoxide, to sublimate into gas. This gas expands rapidly, forming the coma and tails that make comets visually spectacular. But the gas doesn't just drift away passively. It escapes in jets, concentrated streams emerging from active regions on the nucleus. These jets carry momentum. When gas molecules leave the surface, they push against the nucleus, creating a thrust analogous to a rocket exhaust. If the jets are distributed symmetrically around the nucleus, the forces cancel out, and the net acceleration is zero. But if the jets are asymmetric, concentrated on one side, or aligned with the rotation axis, the forces don't cancel, and the object drifts. This is how most cometary trajectories are modelled. Astronomers observe the deviation from a purely gravitational orbit, calculate the magnitude and direction of the acceleration, and then work backward to estimate the outgassing rate and geometry required to produce that acceleration. For 3i Atlas, this process failed. The observed transverse acceleration was 0.43 meters per second, squared in a direction 22 degrees, offset from the expected solar radiation pressure vector. To produce this acceleration with outgassing, the nucleus would need to release gas at a specific rate, in a specific direction, with a specific velocity. A team at the Planetary Science Institute in Arizona ran the numbers. They assumed a nucleus radius of 250 meters and a density of 0.6 grams per cubic centimeter, typical for comets. This gave a mass of roughly 400 million kilograms. To accelerate this mass at 0.43 meters per second squared requires a thrust of approximately 172 kilonewtons. For a gas jet, thrust is proportional to the mass flow rate and the exhaust velocity. The exhaust velocity of sublimating water vapor, heated by sunlight to a temperature of around 250 Kelvin, is roughly 500 meters per second. Plugging this into the rocket equation, the required mass flow rate is about 344 kilograms per second. 344 kilograms per second of water vapor, sustained over multiple days. The team checked whether this was plausible. They estimated the object's surface area, roughly 200,000 square meters, and calculated how much water would need to sublimate per square meter per second to produce the required thrust. The answer was about 1.7 milligrams per square meter per second. This is where the model breaks down. At 3i Atlas's distance from the Sun on July 5th, about 32 million kilometers, the solar flux was approximately 3,000 watts per square meter. Sublimating water ice requires an energy input of roughly 2.8 million joules per kilogram, accounting for both the latent heat of sublimation and the energy needed to lift the gas out of the gravitational well. Using these values, the maximum outgassing rate per square meter is limited by the available solar energy. For a perfectly black surface absorbing all incident sunlight, the maximum rate is about 0.001 kilograms per square meter per second, about 600 times lower than required. Even if the object's surface was optimally oriented, with active regions concentrated on the sunlit side, and even if all the absorbed energy went into sublimation, with zero losses to thermal radiation, the outgassing would fall short by 2 orders of magnitude. The team tried relaxing the assumptions. They increased the nucleus size, lowered the density, assumed a more volatile rich composition, with carbon dioxide instead of water. CO2 sublimates more readily and produces higher exhaust velocities. But even with CO2, the required mass flow rate was still too high by a factor of 10. They ran Monte Carlo simulations, varying all the free parameters within reasonable ranges: nucleus size, albedo, rotation period, active fraction. None of the configurations could reproduce the observed acceleration using purely thermal outgassing. There were two possible interpretations. The first was that the measurements were wrong. Perhaps the astrometric positions were contaminated by systematic errors, small biases in the telescope pointing, or distortions in the reference star catalogue. If the acceleration was actually smaller than reported, the outgassing model might still work. But 3 independent observatories had confirmed the drift, and the most recent data, collected on August 3rd, showed that the acceleration was persisting, if not increasing slightly. The probability of a systematic error affecting all 3 sites in the same way was low. The second interpretation was that the outgassing model was incomplete. Maybe there was a mechanism that hadn't been considered, a way for the object to produce thrust without relying on solar heating alone. Some researchers pointed to the possibility of stored energy. If the nucleus had been heated internally, perhaps by radiogenic decay or tidal friction during a close planetary encounter, it could release trapped gases over time, independent of solar flux. This idea had precedent. In 2019, the interstellar comet 2I Borisov exhibited outgassing that was unusually sustained, even at large distances from the Sun where solar heating should have been negligible. Some models suggested that Borisov's nucleus contained pockets of highly volatile compounds, perhaps carbon monoxide or nitrogen, that could sublimate at very low temperatures, providing a steady gas flow. Could 3I Atlas have similar reservoirs? The problem was that the spectroscopic data didn't support this. If the object were outgassing CO or N2, those molecules would be detectable in the UV spectrum as emission or absorption features. Yet the spectra showed no strong lines from these species. The dominant emission was from ionized magnesium, which doesn't participate in outgassing thrust because it's produced by photoionization of dust grains, not by sublimating ice. On August 5th, a researcher at Caltech proposed a different mechanism: electrostatic repulsion. The idea was that if the nucleus had a significant electric charge, it could repel charged dust grains in the coma. These grains would accelerate away from the nucleus, carrying momentum. By Newton's third law, the nucleus would experience an equal and opposite thrust. The magnitude of this thrust would depend on the charge density and the dust production rate. For typical cometary dust-to-gas ratios, the electrostatic thrust would be negligible. But if 3I Atlas had an unusually high dust content, or if the grains were highly charged due to intense UV exposure, the effect could become significant. The Caltech researcher ran a simulation, modelling the dynamics of charged grains in a cometary coma under the influence of solar wind and solar radiation pressure. The results were intriguing. For certain combinations of grain size and charge, the electrostatic thrust could reach levels comparable to the observed acceleration. But there was a catch. The grains would need to be charged to potentials of several hundred volts, much higher than typical for natural dust. Achieving such high potentials would require either an unusually strong UV flux or a surface with low conductivity that could sustain charge separation over time. Neither condition seemed likely at 3I Atlas's distance from the Sun. By the evening of August 5th, the research community was fragmented. Some held to the outgassing model, arguing that the parameters could be fine-tuned with better data. Others were exploring exotic mechanisms like electrostatic thrust or stored volatiles. A few were privately entertaining the possibility that the acceleration might not be natural at all. That evening, a senior astronomer at the Harvard-Smithsonian Center for Astrophysics circulated a memo titled Alternative Hypotheses for 3I Atlas Acceleration. The memo was cautious, almost apologetic in tone. It acknowledged the difficulty of the problem and the lack of definitive evidence. But it also laid out in sober language what would be required if the object were under deliberate control. To produce the observed acceleration with a propulsion system, the device would need to generate a thrust of 172 kilonewtons. For comparison, a single SpaceX Raptor engine produces 2.3 meganewtons, about 13 times more. But Raptor is a chemical rocket, operating at high temperatures with large propellant flows. An advanced propulsion system, perhaps an ion drive or a nuclear electric engine, could achieve the same thrust with far less mass and power. Ion drives produce thrust by accelerating ions to very high velocities using electric fields. The efficiency is much higher than chemical rockets, but the thrust is lower. NASA's Dawn spacecraft, for example, used an ion drive that produced 92 millinewtons of thrust. To match 3I Atlas's acceleration, you would need an ion drive scaled up by 6 orders of magnitude, a system producing millions of times more thrust than Dawn. This would require massive power sources, likely nuclear reactors and propellant tanks carrying thousands of tons of ionizable material. The engineering was daunting, but not impossible. The memo concluded with a single sentence: "If this object is not natural, it represents a level of technology significantly beyond our current capabilities." The memo wasn't published. It wasn't leaked. It circulated quietly among a few dozen scientists, most of whom read it, nodded, and filed it away. Because the question wasn't just whether 3I Atlas could be artificial. The question was what to do if it was. 19 days to perihelion. The numbers didn't add up. Chapter 8. Shutdown Season. On August 10th, the universe decided to stop cooperating. The Carl G. Jansky Very Large Array, which had provided critical radio observations on July 18th, entered a scheduled maintenance period. The array was being reconfigured from its compact D configuration to the more extended C configuration, a process that involved physically moving each of the 27 dishes along railroad tracks to new positions. This reconfiguration happens 4 times a year and typically lasts about 2 weeks. During that time, the array is offline, unable to observe. The timing was unfortunate. Radio observations had been one of the few ways to probe the ionization state and magnetic properties of 3I Atlas's coma. Without the VLA, researchers would have to rely on smaller radio telescopes with lower sensitivity, or wait until the array came back online in late August, by which point the object would be significantly closer to the Sun and harder to observe. Meanwhile, the European Southern Observatory's Very Large Telescope in Chile faced its own challenges. 2 of the 4 main units were undergoing mirror recoating, a delicate process that involves stripping the reflective aluminum layer from the 8.2-meter primary mirrors and applying a fresh coat. Mirror recoating is essential for maintaining optical quality, but it renders the telescopes unusable for weeks at a time. The scheduling office issued a notice. VLT observing programs would be reduced by approximately 30% through the end of August. And then there was JWST. On August 9th, the James Webb Space Telescope experienced a minor anomaly. One of the spacecraft's reaction wheels, the devices that control the telescope's orientation, reported an unexpected vibration. The anomaly was classified as low risk, but mission controllers decided to pause science operations temporarily while they diagnosed the issue. The pause was expected to last 3 to 5 days. 3 to 5 days might not sound like much, but for a target like 3I Atlas, every day mattered. The object was brightening as it approached perihelion, but its angular separation from the Sun was decreasing. Ground-based telescopes could still track it, but only during narrow windows before dawn or after sunset. JWST, with its deep infrared sensitivity, could observe the object even at small solar elongations, but only if it was operational. The pause stretched into a week. By August the 10th, the observation window was narrowing from all sides. Instruments were down, schedules were full. The object was 16 days from perihelion and beginning to fade into the Sun's glare. This was shutdown season. Not an official term, but a reality of modern astronomy. Telescopes need maintenance. Instruments need recalibration. Spacecraft need rest periods to avoid overheating or mechanical fatigue. And funding cycles don't always align with cosmic opportunities. For the researchers tracking 3I Atlas, the frustration was palpable. On August 11th, a group of astronomers held a video conference to assess their options. The mood was tense. Someone joked that the universe was conspiring against them. Someone else pointed out that Oumuamua had faced similar observational challenges. It had been discovered late, observed sporadically, and ultimately slipped away before anyone could gather definitive data. The difference this time was that 3 Atlas had given more warning. It had been detected earlier, tracked more consistently, and scrutinized with better instruments. Yet the anomalies remained unresolved. The magnesium excess, the transverse acceleration, the 11.4-hour pulse, none of it fit together cleanly. And now, just as the object was approaching its closest point to the Sun, when outgassing should be peaking and spectroscopic signatures should be clearest, the instruments were going dark. One astronomer, a veteran of 3 decades of comet research, summed it up. "We're running out of time and out of options." The group discussed what could be salvaged. Ground-based photometry could continue with smaller telescopes. The Las Cumbres Observatory network was still operational, and several amateur astronomy groups had volunteered their time and equipment. Spectroscopy would be harder, but not impossible. A few observatories with smaller spectrographs could still obtain low-resolution data. Radio observations were the biggest loss. Without the VLA, the ability to probe the coma's ionization state and magnetic interactions was severely limited. A proposal was made to request emergency observing time at the Arecibo Observatory in Puerto Rico, but Arecibo had been decommissioned in 2020 after its main dish collapsed. The loss of that facility was still felt acutely in the planetary science community. Someone suggested the Allen Telescope Array in California, a collection of smaller radio dishes designed for SETI, the search for extraterrestrial intelligence. The ATA wasn't as sensitive as the VLA, but it was operational and could be scheduled more flexibly. A contact was made. The ATA team agreed to allocate a few hours on the night of August 14th. It wasn't much, but it was something. The conversation then turned to the Starship memo. A few people on the call had heard about it, though none had been directly involved in the discussions at SpaceX or NASA. The idea of launching a fast flyby mission was appealing in principle, but the logistical and political barriers seemed insurmountable. One astronomer raised a practical concern. Even if a probe could be launched in time, what would it measure? The flyby would last 90 seconds at best. That was enough time for imaging and spectroscopy, but not enough for detailed surface mapping or in situ analysis. And if the object turned out to be an ordinary comet, the mission would be remembered as an expensive overreaction. Another countered, if the object turned out to be extraordinary, the mission would be remembered as the moment humanity decided to look closely at something that didn't quite fit. The debate was philosophical as much as scientific. How much uncertainty was acceptable before taking action? How much evidence was required before making a bold claim? And who gets to decide what counts as extraordinary? No consensus was reached. The call ended with a plan to continue ground-based observations, coordinate with the Allen Telescope Array, and hope that JWST came back online soon. That night, one of the astronomers stayed up late, scrolling through the latest photometric data. The light curve was still there, pulsing every 11.4 hours. The amplitude was unchanged, the period was stable. She thought about heartbeats again, about rhythms that persist even when everything else is falling apart. She sent an email to the team with the subject line. It's still there, just 3 words. But they carried weight, because despite the shutdowns, despite the maintenance periods, despite the institutional friction and the narrowing window, 3i Atlas was still moving through space, still pulsing, still defying simple explanations, and it was still waiting for someone to understand. 14 days to perihelion. The instrument slept. Chapter 9. The Bend-Back Event. On August 14th, the object did something no one was prepared for. It bent back. The term bend back isn't formal. It's not in the textbooks or the orbital mechanics literature. But it's the best description for what the tracking team observed that morning when they compared the latest astrometric positions to the predicted ephemeris. For the previous 10 days, 3i Atlas had been drifting transversely, sideways relative to its velocity vector, in a direction offset from the expected solar radiation pressure. The drift was small but consistent, accumulating at a rate of 0.43 meters per second squared. The trajectory had curved slightly, bending away from the purely gravitational path, but on August 14th the drift reversed, not completely, not instantly, but measurably. The transverse acceleration component flipped sign, pointing in the opposite direction. Over the course of 6 hours, the object's trajectory curved back toward the original predicted path, as if it were correcting an error. The first astronomer to notice it was at the Magdalena Ridge Observatory in New Mexico. She was reviewing the night's astrometric data, cross-referencing the object's position against the latest JPL Horizons ephemeris, when she saw the deviation. The object was 0.82 arcseconds off from the predicted position. but in the opposite direction from the previous night. She checked the reference star catalogue. She checked the telescope pointing logs. She checked the atmospheric seeing conditions. Everything looked normal. She ran the astrometry reduction pipeline again, using a different set of reference stars. The result was the same. The object had shifted. She sent an email to the Minor Planet Center with the subject line 3I Atlas, possible trajectory reversal, confirm. Within an hour, 2 other observatories responded. Both had observed the object on the night of August 13th of 14. Both confirmed the shift. By noon on August 14th, the data was undeniable. The object's transverse acceleration had changed direction. This was unprecedented. Outgassing-driven accelerations can vary in magnitude as a comet's activity waxes and wanes. They can change direction as the nucleus rotates, exposing different jets to sunlight. But those changes are typically gradual, smeared out over multiple rotations. What the tracking team was seeing on August 14th was more abrupt. The acceleration had reversed within a period shorter than the object's 11.4-hour rotation cycle. A dynamicist at NASA's Jet Propulsion Laboratory ran a quick simulation, modelling how a rotating, outgassing nucleus could produce such a reversal. The scenario required a very specific geometry. 2 active regions on opposite sides of the nucleus, each producing jets of equal strength, with the rotation axis tilted in just the right way to cause the net thrust to flip as the object spun. It was possible, barely. But the timing had to be exact. The rotation period, the jet intensities, and the viewing geometry all needed to align within a narrow parameter space. The odds of this occurring naturally were low, not impossible, but improbable. And there was another problem. If the reversal was due to rotation-modulated outgassing, the effect should repeat every 11.4 hours. The transverse acceleration should oscillate, flipping back and forth with each rotation. But the observations from August 15th showed that the reversal was sustained. The acceleration remained in the new direction, not oscillating, but steady. This ruled out the simple rotation model. By the afternoon of August 14th, the research community was in turmoil. Emails flew back and forth. Some researchers argued for caution, urging everyone to wait for more data before drawing conclusions. Others pointed out that the observation window was closing rapidly. There wasn't time for caution. A few began drafting papers, outlining possible mechanisms and calling for coordinated follow-up observations. One astronomer described the situation as controlled chaos. That evening, the Allen Telescope Array in California began its scheduled observation. The ATA consists of 42 small radio dishes, each 6 meters in diameter, operating as a coordinated interferometer. The array isn't as sensitive as the VLA, but it's fast and flexible, capable of switching targets quickly and monitoring multiple frequencies simultaneously. The observation lasted 4 hours, from 10 p.m. to 2 a.m. Pacific time. The target was faint, barely detectable above the radio noise from the Milky Way and terrestrial interference. But the ATA's signal processing algorithms were optimized for weak time-variable sources, a legacy of its original SETI mission. The preliminary data came in around 3 a.m. There was a detection, weak but present. The radio spectrum showed a faint continuum consistent with thermal emission from dust, along with a narrow spike near 1667 MHz, the hydroxyl H radical line. Hydroxyl is a common cometary emission, produced when water molecules are broken apart by sunlight. The presence of OH confirmed that the object was outgassing, at least to some extent. But the line's intensity was oddly variable. Over the 4-hour observation, the OH emission flickered, rising and falling with a period of roughly 11 hours. This was consistent with rotation-modulated outgassing. But here's what was strange. The OH emission peaked twice during the observation, suggesting 2 active regions on opposite sides of the nucleus. Yet the photometric brightness curve, which was still being tracked by Las Cumbres Observatory, showed only 1 peak per rotation. 2 emission peaks, 1 brightness peak. This mismatch was difficult to explain. If there were 2 outgassing jets, they should both contribute to the scattered sunlight, producing 2 brightness peaks, unless one of the jets was much weaker, or obscured, or oriented in a way that didn't enhance the reflected light. A researcher at MIT proposed a model. Perhaps the object was a contact binary, 2 lobes stuck together, with one lobe bright and inactive, the other dark and actively outgassing. As the object rotated, the bright lobe would dominate the photometric signal, producing one peak. But the outgassing would come from both lobes, producing two OH emission peaks. This model fit some of the data, but it struggled with the bend-back event. For the acceleration to reverse, the outgassing geometry would need to change abruptly. How does a contact binary's geometry change, unless it's not stable? A few researchers began speculating about structural changes. Maybe the object was fragmenting, shedding pieces as tidal forces or thermal stress pulled it apart. Comets do fragment occasionally, especially when they pass close to the Sun or a planet. The breakup of Comet Shoemaker-Levy 9 before its collision with Jupiter in 1994 is the most famous example. But 3 Atlas wasn't under extreme tidal stress. Its perihelion distance was 0.37 AU, about 55 million kilometers from the Sun, closer than Mercury but not close enough to tear a moderately cohesive object apart. And there was no sign of fragmentation in the images. The coma was diffuse but unitary, with no obvious secondary nuclei or debris trails. On the evening of August 15th, a planetary scientist at the University of Colorado ran a different simulation. Instead of modelling the object as a passive body responding to solar forces, she modelled it as an active system capable of adjusting its thrust. She parameterized the simulation with a simple control algorithm. If the object's trajectory deviates from a target path, apply a corrective thrust to bend it back. The simulation matched the observations almost perfectly. She stared at the results for a long time, then she closed the file without saving it, because the implications were too large. If the object was correcting its trajectory, if it was responding to deviations with deliberate adjustments, it wasn't just drifting, it was navigating. She didn't share the simulation. She didn't send an email. She just sat there, in the dim glow of her computer screen, thinking about what it meant if something out there was steering. On August 16th, the magnesium emission data from Gemini was reprocessed. The analysis confirmed that the MG2 line had also changed. Around the time of the bend-back event, the line's intensity had briefly doubled, then returned to its previous level. A burst, a flare, a pulse of energy. The correlation was undeniable. The trajectory reversal and the magnesium spike occurred within hours of each other. Some researchers interpreted this as evidence of a sudden outgassing event, perhaps a small landslide or sublimation burst that triggered both the emission and the acceleration change. Others saw it as more evidence that the object was interacting with the solar wind in unexpected ways, possibly through electromagnetic forces. And a very small number saw it as evidence of control, a deliberate maneuver, a course correction. No one said this publicly, but in private messages, in late-night emails, in conversations that weren't recorded, the question began to circulate. What if it knows where it's going? 12 days to perihelion. The object bent back. Chapter 10. Sherlock, Pixel, and the Ghost Lines. On August 20th, the spectroscopic data pipeline did something it wasn't supposed to do. It found a line that shouldn't exist. The discovery came from an unexpected source, not from a telescope pointed at the sky, but from a data processing algorithm originally designed for Mars. Sherlock and Pixel are 2 instruments aboard NASA's Perseverance rover, currently exploring Jezero Crater on Mars. Sherlock stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. Pixel stands for Planetary Instrument for X-ray Lithochemistry. Both are spectroscopic tools designed to analyze the chemical composition of Martian rocks and soil at microscopic scales. But spectroscopy is spectroscopy. The principles that allow Sherlock and Pixel to identify minerals on Mars also apply to cometary comae. Light interacts with matter in predictable ways, producing absorption or emission features at specific wavelengths. The challenge is extracting those features from noisy data contaminated by background signals, instrumental artifacts, and cosmic rays. Over the past decade, the Perseverance mission team has developed sophisticated algorithms for cleaning up spectroscopic data, removing noise, and identifying faint spectral lines that might otherwise be lost in the background. These algorithms use machine learning techniques trained on thousands of laboratory spectra, teaching the software to recognize the patterns associated with real chemical signatures and distinguish them from random fluctuations. On August 18th, a postdoctoral researcher at Caltech had an idea. She was part of the Pixel team, but she was also following the 3i Atlas observations. She wondered whether the Pixel data pipeline, specifically the spectral deconvolution algorithm, could be applied to the Gemini and VLT spectra of 3i Atlas. She downloaded the raw spectral data from the ESO archive, converted it into a format compatible with the Pixel pipeline, and ran it through the noise reduction and line identification algorithms. The pipeline took about 6 hours to process the data. When it finished, it flagged 43 spectral features as statistically significant. Most were familiar: magnesium, oxygen, carbon, sodium. But 3 were unidentified. 3 narrow emission lines at wavelengths that didn't match any known atomic or molecular transitions in the spectroscopic databases. The first line was at 312.4 nanometers in the ultraviolet. The second was at 487.9 nanometers in the blue-green. The third was at 612.8 nanometers in the orange-red. None of these wavelengths corresponded to common cometary emissions. None matched laboratory spectra of typical dust minerals or gas phase molecules. The researcher cross-referenced them against comprehensive atomic line databases, including NIST and HITRAN. No matches. She checked the instrumental calibration files, looking for possible artifacts. Spectrographs can produce spurious lines due to reflections, filter ghosts, or scattered light within the optical system. But these artifacts are usually predictable. They occur at specific wavelengths related to the instrument's design, and they're present in calibration exposures taken without any target. The 3 lines weren't in the calibration data. She ran the pipeline on archival spectra of other comets, observed with the same instruments. The lines didn't appear. On the morning of August 20th, she sent an email to the 3i Atlas tracking team with the subject line, "Possible unidentified lines. Need independent confirmation." The response was swift. Within hours, 3 other researchers had downloaded the same raw data and run their own analyses to confirm the presence of the lines. One reported marginal detections, signals that were just at the edge of statistical significance. By the afternoon, a 4th astronomer had obtained new spectra using the Nordic Optical Telescope. The 312.4 nanometer line was present, the 487.9 nanometer line was present, the 612.8 nanometer line was absent. This was both encouraging and frustrating. Encouraging because 2 of the lines had been independently confirmed. Frustrating because the third line, the one in the orange-red, appeared only in the older data. It had vanished. Transient spectral lines are not unheard of in cometary science. Some emissions are produced by short-lived radicals or ions that form and dissociate quickly as the comet evolves, but transient lines usually correlate with specific outgassing events or solar activity. The 612.8 nanometer line had appeared on August 11th, persisted for about 36 hours, and then disappeared. What happened on August 11th? The team reviewed the observation logs. August 11th was the day after the JWST anomaly began, when most major instruments were offline or in maintenance. It was also 3 days before the bend-back event. Could the line have been related to the trajectory reversal? The timing was suggestive, but correlation isn't causation, and without additional data, it was impossible to determine whether the line was real or a processing artifact. One astronomer proposed a test. If the line was real and associated with a specific physical process, it should have a natural width, a small spread in wavelength due to thermal motion and collisions among the emitting atoms or molecules. Measuring this width requires high-resolution spectroscopy with instruments capable of resolving features narrower than 1/10 of a nanometer. The Gemini spectra had a resolution of about 1/2 a nanometer, not quite high enough. The VLT spectra were better, around 0.2 nanometers. The researcher who had first identified the lines went back to the VLT data and zoomed in on the 312.4 nanometer feature. The line was narrow, very narrow, barely resolved by the instrument. This implied either a very cold gas, temperatures below 50 Kelvin, or a very specific emission process with little thermal broadening. Both scenarios were unusual. Cometary comae are typically warm, heated by sunlight to temperatures of several hundred Kelvin, and most emission processes involve collisions or radiative cascades that naturally broaden the lines. On the evening of August 20th, a spectroscopist at the University of Arizona proposed a different explanation. What if the lines weren't emissions from gas, but reflections from solid particles? Certain minerals and synthetic materials can produce narrow spectral features due to electronic transitions in their crystal structures. These features are sometimes called color centers or defect lines, and they're used in gemology and materials science to identify specific compounds. If 3 atlases coma contained dust grains with unusual mineralogy, perhaps grains formed in a different stellar environment with compositions unlike anything in our solar system, those grains could produce narrow reflection lines at unexpected wavelengths. This hypothesis was testable. Reflection lines should be polarized, because the scattered light preferentially aligns with the orientation of the reflecting particles. Emission lines, by contrast, are usually unpolarized unless the emitting gas is in a strong magnetic field. Unfortunately, none of the spectroscopic observations had included polarimetry. That data simply didn't exist. On August 21st, a request was submitted to the Gemini Observatory for follow-up spectropolarimetry. The request was flagged as high priority, given the narrowing observation window. A decision would come within 24 hours. Meanwhile, the 3 unidentified lines became known, informally, as the ghost lines. The name stuck. It captured the essence of what made them so unsettling. They were there, and then they weren't. They appeared in some datasets, but not others. They defied easy classification, and they hinted at processes that weren't part of the standard cometry playbook. One astronomer, late at night, scrolling through the spectral plots on her screen, thought about all the things humans have seen in the sky that defied explanation at first. Ball lightning, sprites and elves, auroras before anyone understood magnetospheres. The universe is full of phenomena that seem ghostly until we learn their language. Maybe the ghost lines were just another dialect, another process waiting to be understood. Or maybe they were something else, a signal, a marker, a breadcrumb, left by something that knew we were watching. She closed her laptop. She didn't want to think about that. 10 days to perihelion. The ghost lines flickered. Chapter 11. Radio Silence That Speaks On. August 26th, the Very Large Array came back online. The reconfiguration was complete, the dishes were repositioned, and the system was ready for science operations. A proposal for emergency observing time, submitted on August 22nd, had been approved. The VLA would observe 3I Atlas on the night of August 27th to 28, with 8 hours of dedicated time, twice as much as the July observation. The goal was to search for radio emissions associated with solar wind interactions. When a comet's coma encounters the solar wind, a supersonic stream of charged particles flowing outward from the Sun, the interaction can generate shock waves, magnetic field compressions, and regions of heated plasma. These processes produce radio emissions, typically in the form of broad continuum radiation, or narrow bursts at specific frequencies. The intensity and spectrum of these emissions depend on the comet's outgassing rate, the density of the solar wind, and the strength of the local magnetic field. For an active comet like Hale-Bopp or Hyakutake, the radio emissions can be quite strong, detectable even with small radio telescopes. For a less active object like 3I Atlas, the emissions would be faint, requiring the sensitivity of a large array like the VLA. On August 26th, a coronal mass ejection erupted from the Sun. The CME was classified as moderate, not strong enough to threaten satellites or power grids on Earth, but significant enough to enhance the solar wind for a few days. The associated shock wave and magnetic flux rope propagated outward at roughly 600 km per second, a bit faster than the ambient solar wind. The tracking team ran a quick calculation. The CME would reach Earth's orbit in about 60 hours, arriving on August 28th. It would cross 3I Atlas's position a few hours earlier, around August 27th. This was fortuitous. If the object was going to interact with the solar wind, a CME-enhanced solar wind would amplify the effect, making the radio emission stronger and easier to detect. The VLA observation was scheduled to begin at 10:05 p.m. on August 27th, just as the CME was expected to reach the object. It was, in the words of one astronomer, a lucky alignment. The observation began as planned. The VLA's 27 dishes tracked 3I Atlas across the night sky, tuned to frequencies between 1 and 18 GHz. The array operated in its most sensitive mode, with long integration times to maximize signal-to-noise. The data was processed in real time, with preliminary spectra appearing on the monitors within minutes of each integration. The team watched the data stream in, waiting for the telltale signs of solar-wind interaction, broadband continuum emission, enhanced ionization lines, or transient bursts. Hours passed. The CME arrived on schedule, swept past the object, and continued toward Earth. But the radio data remained quiet. No broadband emission, no ionization lines, no bursts, just faint thermal noise from the dust coma, barely above the detection threshold. By 2 a.m., the team was puzzled. The solar-wind interaction should have been obvious. The CME's passage should have lit up the radio spectrum, yet there was nothing. One possibility was that the object's outgassing rate was lower than expected, reducing the size and density of the coma. A thin coma wouldn't interact strongly with the solar wind, and the radio emissions would be correspondingly weak. But optical observations from the same night showed that the coma was still visible, still extended. The dust production hadn't dropped. Another possibility was that the object's coma was unusually transparent to the solar wind, allowing the charged particles to pass through without significant deceleration or heating. This could occur if the coma was composed of large dust grains that didn't couple efficiently to the magnetic field, or if the gas density was too low to form a shock wave. But this explanation struggled with the photometric data. If the coma was transparent to the solar wind, it should also be transparent to sunlight, producing a fainter optical signal. Yet the object's brightness was consistent with a normal dusty coma. By dawn on August 28th, the team had reviewed the data 3 times. There was no error. The radio silence was real. This absence became the subject of intense debate over the following days. In science, null results are often as important as positive detections. They constrain what's possible, ruling out certain hypotheses and narrowing the parameter space. But this null result was strange because it contradicted expectations. Given the object's optical appearance, the solar wind conditions, and the sensitivity of the VLA, there should have been a detection. The fact that there wasn't suggested that something about 3I Atlas was different. On August 29th, a plasma physicist at the University of Maryland proposed a hypothesis. What if the object's coma was electrically neutral, not just weakly ionized, but truly neutral, with no net charge separation? Most cometary comae contain a mix of neutral molecules and ions. The ions are produced by solar UV photons and by charge exchange with the solar wind. These ions interact with the solar wind's magnetic field, creating the conditions for shock waves and radio emissions. But if the coma contained unusually efficient recombination processes, mechanisms that quickly reunite ions and electrons into neutral molecules, the ionization fraction could be suppressed. This would require a specific chemical environment, perhaps one involving metal vapors or organic compounds that act as recombination catalysts. Such chemistries are rare but not impossible. The physicist ran a simulation, modeling the ionization and recombination dynamics in a coma with elevated magnesium content. The results were intriguing. Magnesium ions are relatively heavy and have complex electron configurations that facilitate recombination. In a magnesium-rich coma, the ionization fraction could be reduced by a factor of 10 or more compared to a typical water-dominated coma. This could explain the radio silence. With fewer ions, the solar wind interaction would be weaker, and the radio emissions would drop below the detection threshold. But it didn't explain the optical magnesium emission. If the ions were recombining so efficiently, where was the bright Sasaki-2 line coming from? The physicist suggested a 2-component model: a cold, neutral outer coma where recombination dominates, and a hot, ionized inner coma close to the nucleus where ionization rates are higher. The Magnesium emission would come from the inner region, while the radio silence would reflect the outer region's neutrality. This model was plausible, but it required a very specific coma structure, one that hadn't been observed in any other comet. On August 30th, another explanation surfaced. A geophysicist at UCLA, who had been following the 3I Atlas observations out of curiosity, pointed out that certain spacecraft use magnetic shielding to deflect the solar wind. The concept, though still theoretical for human missions, involves generating a strong magnetic field around the spacecraft to redirect incoming charged particles, reducing radiation exposure. If 3I Atlas had an intrinsic magnetic field, either from a magnetized core or from electrical currents in the coma, it could deflect the solar wind before it reached the dense inner coma. This would suppress shock formation and radio emissions. The idea was immediately controversial. Natural objects like comets don't have intrinsic magnetic fields strong enough to affect the solar wind. The field would need to be on the order of microteslars, comparable to Earth's magnetic field, which requires either a liquid metallic core or sustained electrical currents, neither of which are expected in a small, cold body. But the geophysicist pointed out that the magnesium emission and the radio silence could both be explained if the object was generating such a field. Electrical currents in a magnesium-rich plasma could produce a magnetic field through dynamo effects, similar to the processes that generate Earth's magnetosphere. This hypothesis was speculative, very speculative, but it was testable. If the object had a magnetic field, it would distort the solar wind flow around the coma, creating a bow shock upstream and a magnetotail downstream. These structures could be detected through remote sensing of solar wind protons or through direct measurements by spacecraft, if any happened to be nearby. Unfortunately, no spacecraft were nearby. On the evening of August 30th, the tracking team held another video call. The radio silence was discussed at length. Some researchers argued that the null result was simply due to low activity. The object was less vigorous than expected, and there was nothing more to it. Others found the silence troubling, especially when combined with the other anomalies. One astronomer summarized the situation. We have an object that looks like a comet, moves like a comet, but doesn't interact with the solar wind like a comet. We have bright magnesium emissions but weak water signatures. We have a repeating photometric pulse that correlates with trajectory corrections, and now we have radio silence during a CME passage. He paused. Individually, each of these could be explained, but together? No one finished the sentence, because finishing it meant confronting the possibility that the object wasn't following the rules, that it was doing something no natural comet should do. The call ended without resolution. But the silence lingered. Not just the radio silence from the VLA data, but the silence in the room, the unspoken tension between what the data seemed to suggest and what science allowed them to say. 8 days to perihelion. The silence spoke. Chapter 12. The alignment of 3. On September the 2nd, the geometry shifted. At 1437 Universal Time, Earth, the Sun, and 3 of He Atlas came into alignment within a narrow angular corridor, a configuration known as syzygy, though not a perfect one. The object wasn't directly between Earth and the Sun, but the angle had closed to less than 12 degrees. This alignment had been predicted months in advance, and orbital dynamicists had flagged it as a window of interest. The reason had to do with the light travel time and trajectory sensitivity. When observing a moving object, astronomers don't see where the object is now. They see where it was when the light left its surface. For 3I Atlas, at a distance of approximately 27 million kilometers on September 2nd, the light travel time was about 90 seconds. This delay is usually negligible, but it becomes important when measuring the object's position to sub-arc-second precision. During syzygy, the geometry amplifies small trajectory deviations. If the object's velocity changes even slightly, say by a few centimeters per second, that change produces a measurable shift in the observed position over the course of a few hours. The effect is most pronounced when the object, Earth and Sun, are nearly aligned, because the line of sight is nearly parallel to the object's velocity vector. This amplification allows astronomers to detect tiny accelerations that would be invisible at other geometries. On the night of September 2nd, 3 observatories coordinated a simultaneous astrometric campaign. The goal was to measure 3I Atlas's position with the highest possible accuracy, using the syzygy geometry to search for any residual non-gravitational accelerations. The results came in the following morning. The object's position was off from the predicted ephemeris by 1.3 arc-seconds. This was larger than the measurement uncertainty, which was estimated at 0.2 arc-seconds. The deviation corresponded to a velocity change of approximately 8 centimeters per second over the previous 24 hours. But here's what was remarkable. The direction of the deviation had changed again. After the bend-back event on August 14th, the transverse acceleration had stabilized in a new direction, roughly perpendicular to the original drift. It had remained in that configuration for 2 weeks. But on September the 2nd, as the syzygy alignment reached its peak, the acceleration shifted once more. This time, the new direction pointed almost exactly along the line connecting 3I Atlas to the Sun. a radial acceleration, either toward the Sun or away from it. The team ran diagnostics to rule out systematic errors. They checked for telescope-pointing biases, atmospheric refraction effects, and errors in the reference star catalogue. Everything checked out. The acceleration was real. A radial acceleration is easier to explain than a transverse one. Solar radiation pressure naturally produces a radial force, pushing objects away from the Sun. Outgassing can also produce radial thrust, either augmenting or opposing the radiation pressure. But the magnitude of the observed acceleration, 8 centimeters per second over 24 hours, was still too large to be explained by radiation pressure alone. One researcher calculated the required radiation pressure force. For an object with a radius of 250 meters and a typical albedo, the solar radiation pressure at 0.37 AU would produce an acceleration of roughly 10 to the minus 6 meters per second squared, about 100 times smaller than observed. Outgassing could make up the difference. But once again, the outgassing rate would need to be implausibly high, and the water signatures in the optical spectrum remained weak. On September 3rd, a group of dynamicists ran a series of simulations, exploring whether the syzygy geometry itself could explain the acceleration. One hypothesis was that the alignment increased the solar wind pressure on the object, creating a temporary boost in the drag force. But the solar wind pressure is too weak to produce the observed effect, even during a CME event. Another hypothesis involved tidal forces. When the object is aligned with Earth and the Sun, the gravitational pull from both bodies can create a differential force across the object's diameter. For a small, weak body, these tidal forces could trigger structural changes, fractures, collapses, or shifts in internal mass distribution that alter the outgassing geometry. The simulations showed that tidal forces at 3I Atlas's distance were negligible. The tidal acceleration was on the order of 10 to the minus 12 meters per second squared, far too small to matter. On the evening of September 3rd, one astronomer suggested a different interpretation. What if the object was responding to the alignment, not mechanically, not gravitationally, but informationally? If the object were under deliberate control, if it had sensors and algorithms capable of determining its position relative to Earth and the Sun, it might adjust its trajectory during specific geometric configurations. The syzygy alignment would be an ideal time for such an adjustment, because the amplified sensitivity would make small changes easier to detect and correct. This was speculation of the highest order. It required not just intelligence, but intent, a purpose. No one wanted to write that down, but in private conversations the idea circulated, because the timing was too precise. The acceleration shifts had occurred during the bend-back event on August 14th, and now during the syzygy on September 2nd. Both were geometrically significant moments, windows where trajectory corrections would be most effective. If the object was natural, the timing was a coincidence. If it wasn't. On September 4th, a senior astronomer at the Lowell Observatory drafted an email to the team. The subject line was, 3 points of alignment. In the email, she outlined the sequence of events. The initial transverse drift detected in early July, the bend back on August 14th, and the radial shift on September 2nd. She plotted the acceleration vectors on a diagram, showing how each one pointed in a different direction, but always seemed to bring the object closer to a specific target trajectory. She didn't say what the target was. She didn't need to. The implication was clear. If you plotted the trajectory forward, accounting for all the observed corrections, the object wasn't just passing through the solar system. It was threading a needle, adjusting its path to fly within a precise corridor defined by Earth, the Sun, and something beyond. The email ended with a single question. Are we seeing course corrections? The responses were mixed. Some dismissed it as overinterpretation. Others asked for more analysis. A few replied with single-word messages. Maybe. On September 5th, the Gemini Observatory obtained new spectroscopy. The magnesium line was still present, but its intensity had dropped by about 30% compared to the previous week. The object was dimming as it moved closer to the Sun's glare, but the change in magnesium emission was steeper than expected based on photometric trends. Could the outgassing be winding down, or was the object conserving resources, reducing its activity as it approached perihelion? That night, the Las Cumbres Observatory network captured the light curve. The 11.4-hour pulse was still there, but the amplitude had decreased slightly. The object was still rotating, still pulsing, but the contrast between bright and dim phases was less pronounced. One astronomer described it as quieting down. Another said it sounded like the object was preparing. Preparing for what? 6 days to perihelion. The Alignment Held, Chapter 13, The Data We Almost Lost. On September 8th, the Sun decided to interfere. At 11:23 Universal Time, a solar flare erupted from an active region near the Sun's equator. The flare was classified as M5.4, moderate on the logarithmic scale that ranks solar flares from A-class, weakest, to X-class, strongest. M-class flares are common during solar maximum, occurring several times per month. They produce bursts of X-rays and ultraviolet light, along with enhanced solar wind and magnetic disturbances. For most astronomical observations, M-class flares are a nuisance. They increase radio noise, ionize Earth's atmosphere, and can temporarily disrupt satellite communications. But they're rarely catastrophic. Observations can be paused, data can be corrected, and science continues. But on September 8th, the timing was critical. Several ground-based observatories had planned coordinated spectroscopic observations of 3I Atlas, aiming to capture the object's emission lines during the final days before it disappeared into the Sun's glare. The observation window was narrow, only a few hours after sunset when the object was high enough above the horizon to be visible, but still far enough from the Sun to avoid scattered light. The flare peaked just as the observations were scheduled to begin. Within minutes, the ionosphere above several observation sites became turbulent, scattering radio waves and degrading the transparency of the atmosphere to ultraviolet light. Ground-based spectrographs, especially those operating in the UV, struggled to detect faint signals through the ionospheric distortion. At the Gemini Observatory in Hawaii, the scheduled observation was delayed by an hour, waiting for the ionosphere to settle. At the Nordic Optical Telescope in the Canary Islands, the observation was cancelled entirely. The sky conditions were too poor to justify the telescope time, but at the Magellan telescopes in Chile, the team decided to proceed. The Magellan telescopes consist of two 6.5-metre mirrors located at the Las Campanas Observatory in the Atacama Desert. The site is one of the best in the world for optical astronomy, with dark skies, dry air, and minimal light pollution. Even during a solar flare, the conditions at Las Campanas are often better than most other observatories. The observation began at 23:45 local time, about 2 hours after the flare peaked. The object was low on the western horizon, only 20 degrees above the skyline. The spectrograph was configured for high resolution, targeting the ultraviolet and blue regions where the magnesium and ghost lines had been detected. The integration time was set to 30 minutes, long enough to collect sufficient photons but short enough to avoid excessive atmospheric distortion. The spectrograph's CCD detector ticked away, accumulating light pixel by pixel. Halfway through the integration, the solar wind arrived. The flare's X-rays had reached Earth in just 8 minutes, travelling at the speed of light. But the associated coronal mass ejection, a cloud of magnetized plasma ejected from the Sun, travelled much slower, about 700 kilometers per second. It took roughly 14 hours to cross the Sun-Earth distance, arriving at Earth's magnetosphere around 2 a.m. on September the 9th. The impact triggered a geomagnetic storm, classified as G2 on a 5-point scale. Auroras flared over Scandinavia and Canada. Radio communications were disrupted, and the ionosphere, which had just begun to settle after the flare, lit up again with turbulence. At Las Campanas, the sky conditions deteriorated rapidly. Clouds of ionized particles in the upper atmosphere scattered the incoming starlight, adding a hazy glow to the background. The spectrograph's signal-to-noise ratio began to drop. The observer, monitoring the data in real time, faced a decision: abort the observation and save the telescope time, or continue and hope the data could be salvaged. She chose to continue. The integration finished at 0.17 local time. The raw spectrum was downloaded from the detector and displayed on the monitor. At first glance, it looked terrible. The background was high, the signal was faint, and several spectral regions were saturated by ionospheric emission lines. But buried in the noise, there was data. The observer spent the next 4 hours processing the spectrum, carefully subtracting the background, masking the saturated regions and applying noise reduction algorithms. By dawn, she had extracted a usable spectrum covering the range from 290 to 550 nanometers, and there it was, the magnesium line at 279.6 nanometers, still present, still bright. But there was more. At 312.4 nanometers, the wavelength of the first ghost line, there was a clear emission feature. Narrow, bright, unmistakable. She cross-referenced the wavelength against the previous detections. It matched to within the instrument's resolution. The ghost line was back. She sent an email to the team with the subject line, "Got it," despite everything. The response was immediate. Within hours, other astronomers were analysing the spectrum, confirming the detection, cross-checking the calibration. The line was real, and it had reappeared after vanishing for nearly a month. But here's what made the detection even more significant. The line's intensity had changed. In the August 11th observation, the 312.4 nanometer line had been faint, barely above the noise. In the September 8th observation, it was strong, about twice as bright as the magnesium line. What had changed? One possibility was that the line's intensity varied with the object's activity level. As the object approached perihelion, solar heating increased, perhaps triggering processes that enhanced the emission. But this explanation struggled with the fact that the magnesium line had dimmed, not brightened. Another possibility was that the emission came from a specific region of the object that was now facing Earth. If the ghost line was produced by a localized source, a hotspot, a vent, or a surface feature, its brightness would vary as the object rotated. But the rotation period was 11.4 hours. For the line to go from undetectable to prominent over the course of 3 weeks, the rotational phase would need to have aligned perfectly with the observation window. Possible, but improbable. On September 9th, a spectroscopist at the European Southern Observatory ran a detailed analysis of the line's profile. She measured its width, its shape, and its centroid wavelength. The line was narrow, unresolved by the spectrograph, which had a resolution of about 0.15 nanometers. This placed an upper limit on the line's natural width, less than 0.1 nanometers. For a gas emission line, this would imply temperatures below 20 Kelvin, colder than the cosmic microwave background. Impossible for a gas in a cometary coma. For a reflection or fluorescence line, the narrow width could be consistent with solid particles or molecular crystals with well-defined electronic transitions. But identifying the material would require laboratory spectroscopy, matching the observed wavelength to synthetic spectra of candidate compounds. She compiled a list of possibilities: rare earth oxides, transition metal complexes, organic chromophores. None matched the 312.4 nanometer wavelength. On September 10th, another astronomer suggested checking databases outside the traditional astronomical references. Perhaps the line corresponded to a synthetic material, something manufactured rather than naturally occurring. Industrial phosphors, laser-gain media, and semiconductor materials often have narrow emission lines at specific wavelengths. The search turned up 2 matches: a europium-doped phosphor used in fluorescent lighting and a synthetic dye used in biomedical imaging. Both emitted near 312 nanometers, but neither was expected to exist in a cometary coma. The discussion became increasingly surreal. Were they seriously suggesting that 3I Atlas contained industrial phosphors or biomedical dyes? No, not seriously. But the fact that the question was even raised showed how far outside the normal bounds of comet science the object had pushed them. On the evening of September 10th, the team held a final video call before perihelion. The topic was simple: what do we know, and what don't we know? The list of knowns was short. The object was real. It was moving on a hyperbolic trajectory. It exhibited a repeating photometric pulse, a magnesium emission anomaly, transient ghost lines, trajectory corrections, and radio silence during solar-wind interactions. The list of unknowns was longer. What caused the acceleration? What produced the ghost lines? Why was the magnesium ratio so high? Was the object natural or something else? No one had answers, but everyone agreed on one thing. They had witnessed something extraordinary, something that didn't fit the models, something that demanded further study. If only there had been more time. 4 days to perihelion, the data survived. Chapter 14. What motion chooses to tell us. On September 14th, 3 Atlas reached perihelion, its closest approach to the Sun. At 8:12 Universal Time, the object crossed the threshold, 0.37 astronomical units, roughly 55 million kilometers from the Sun's surface. Closer than Mercury's orbit. Close enough that surface temperatures, if the object were dark and absorbing, would reach several hundred degrees Celsius. Close enough that any remaining volatiles should have been sublimating vigorously, producing a bright active coma. But the object was faint, fainter than expected. The last usable images, captured 2 days earlier by the Gemini Observatory, showed a dim coma and a barely detectable nucleus. The photometric brightness had dropped by nearly half a magnitude over the previous week, even as the object moved closer to the Sun. This was the opposite of typical cometary behaviour, where brightness increases as the comet heats up and outgassing intensifies. It was as if the object had gone quiet. By September 15th, 3 Atlas had entered the Sun's glare, the region of the sky where the Sun's brightness overwhelms faint objects, making ground-based observation impossible. For the next several weeks, the object would be invisible from Earth. When it emerged on the far side of the Sun in mid-October, it would be receding, dimmer, and more difficult to observe. The best observation window was over. The tracking team gathered their data, compiled their notes, and began drafting papers. Some focused on the magnesium anomaly. Others analysed the trajectory corrections. A few tackled the ghost lines. Each paper was careful, measured, couched in the language of uncertainty and further investigation. But in private, the conversations were different. On September 16th, a small group of astronomers held an informal call. No agenda, no minutes, just a chance to talk openly about what they had seen and what it might mean. One astronomer began. Let's assume, just for a moment, that the object was under control, not natural, not a comet. What would that change? There was a long pause. It would mean, another said slowly, that something crossed the distance between stars, that something built a machine capable of navigating the solar system, and that we watched it adjust its trajectory in real time. But we don't have proof, a third added. Every anomaly we observed can be explained individually by natural processes, unlikely processes, but not impossible. True, but that's always the problem with extraordinary claims. You never get proof. You get a pile of improbable coincidences, and you have to decide whether the simplest explanation is that they're all unrelated or that there's a unifying cause. Occam's razor. Exactly. The simplest explanation is usually the correct one. But what's simpler? A comet with a 1 in 20,000 composition, a repeating pulse that correlates with trajectory corrections, ghost lines from unknown chemistry, and radio silence during a solar-wind interaction, all by chance, or one hypothesis that ties them together. Another pause. If it's the latter, what do we do about it? We keep observing, we publish the data, we let the scientific community weigh in, and we hope someone smarter than us figures it out. And if no one does, then it becomes one of those mysteries, like the wow signal, or fast radio bursts before we understood them, something that lives in the literature, unanswered, waiting for the next generation. The call ended without resolution, but there was a sense of closure. They had done their job. They had followed the data, explored the possibilities, and documented the mystery. Whatever 3I Atlas was, it had given them a story worth telling. On September 18th, the first paper was submitted to the Astrophysical Journal. The title was modest: Non-Gravitational Accelerations and Chemical Anomalies in Interstellar Object 3I Atlas. The abstract summarized the observations, noted the statistical significance of the anomalies, and concluded with the standard phrase, "Further observations are needed to constrain the physical mechanisms responsible." Other papers followed over the next few weeks. One focused on the magnesium emission, comparing it to archival comet data. Another analysed the photometric pulse, proposing a contact binary model with asymmetric albedo. A third examined the radio data, discussing the implications of the null detection during the CME event. None of the papers mentioned artificial origin. The phrase was too loaded, too prone to misinterpretation. But the data was there, available for anyone to analyse. On October the 2nd, 3R's Atlas emerged from behind the Sun. Amateur astronomers in Australia were the first to spot it, now a faint magnitude 18.5 object receding at 43 kilometers per second. The coma was barely visible. The nucleus was a faint point of light, indistinguishable from a distant star. A few observatories captured follow-up images, confirming the object's trajectory. The orbit matched the predictions almost perfectly, with only minor residuals attributable to the earlier non-gravitational accelerations. There were no new surprises, no additional anomalies. By mid-October, the object was too faint for most telescopes. By November, it had faded below magnitude 20, accessible only to the largest observatories with long integration times. By December, it was gone, a speck of light vanishing into the interstellar void, unreachable and unrecoverable. The story of 3I Atlas became part of the astronomical literature, a footnote in the catalogue of interstellar objects, a case study in the challenges of rapid response observation, a reminder that the universe still holds secrets that resist easy explanation. But for those who had followed it closely, who had watched the light curve's pulse and the trajectory bend, the object left a deeper impression. One astronomer, reflecting on the experience months later, described it this way: "We spend our careers looking at the sky, measuring light, building models. Most of the time the universe behaves, it follows the rules. But every once in a while you see something that doesn't quite fit. Something that makes you stop and wonder whether the rules are complete." She paused. 3I Atlas was one of those things, and the fact that we may never know what it was, that's part of the story, because science isn't always about answers. Sometimes it's about learning to live with questions. When motion breaks the law. On a cold January evening in 2025, a graduate student at Caltech was reviewing archival data from the Pan-STARRS survey. She was searching for faint, fast-moving objects, anything that might be an undiscovered interstellar visitor from the previous year's observing season. Around midnight, she noticed something odd, a faint streak in an image from August 2024, right ascension, 13 hours, 23 minutes, declination, -8 degrees. She cross-referenced the coordinates against known object databases. No match. She checked the timing. The image was taken on August 14, 2024, the day of the bend-back event. She plotted the object's position on a sky chart. It was close, very close to 3I Atlas's predicted location. But the motion was wrong. The streak wasn't parallel to 3I Atlas's trajectory. It was perpendicular. She ran astrometry on the streak, measuring its length and orientation. The object had moved roughly 2 arc minutes during the 30-second exposure. That translated to an angular velocity of 4 arc seconds per second, consistent with something in the inner solar system, not an interstellar object. She sent an email to her advisor with the subject line, "Possible secondary objects near 3I Atlas?" The advisor replied within an hour. "Probably just an asteroid. Check the asteroid database." She checked. No known asteroid matched the position and time. She ran the numbers again. The object, if real, would have been within a few 100,000 kilometers of 3I Atlas. Not a coincidence. Not at that distance and time. She drafted a longer email detailing the detection and asking whether anyone else had seen it. Then she hesitated, because if the streak was real, it meant something had been near 3I Atlas on August 14th. Something moving independently. Something that wasn't in any catalogue. She saved the draft. She didn't send it. Not yet. Because some questions, once asked, can't be unasked. And some data, once shared, changes everything. She closed her laptop. She looked out the window at the night sky. Vast, dark, and full of things we haven't yet learned to see. And somewhere, far beyond the orbit of Neptune, 3I Atlas continued its journey. Silent, unreachable, moving through the space between stars at tens of kilometers per second. When motion breaks the law, we follow. But sometimes motion chooses not to be followed. This is not science fiction. This is what we know. This is what we don't. And this is the space between them where mysteries live.